Yeah, this is topological.
No, I'm asking you.
No,
With respect to the metric.
Okay, with respect to the metric, the hyperbolic metric, you mean? Yes, the surfaces has very different shapes. The surface may have very different shapes. Yes.
Is there a classification for these types as well?
Yes. So I explain what is the classification? What is the
Teichmuller space.
huh?
The Teichmuller space.
Yes, exact. The Teichmuller space is the space of all different shapes. When two shapes are the same, when they are isometric, then they are in the same point in the Teichmuller space.
So the 16 minus 6.
Yes.
It covers this as well.
It covers this, yes. It is a space of parameters.
Okay.
It is this space of parameters. Yes.
Yeah, so let's start today's lecture. That's a 2 hour lecture with a small break, and there will be a group photo session at 4 p.m. and please call all your friends who are registered and are not here.
Okay, thank you. So I answer again to this question here. For instance, now we are talking about surfaces not only topological but equipped with some hyperbolic structure which we cannot visualize. But some of the properties we can represent on the picture here. So this is a surface of genus 3 with a long tube here, very long tube. And let me take another surface here. With a long tube here. In fact, they represent different points in Teichmuller space, even if they are isometric. Even if I turn this surface from left to right, and I can put it isometrically on the other one, they represent different points. And this is because of the following notion. In fact, there's a notion of marking of a surface. It could be of a topological surface or geometric, say hyperbolic surface, or even if it's on the torus, I have the marking of the torus. So let me tell you what is the marking. What is the marking of a surface? Because this plays an important role here. So this is a fixed topological. I take a fixed topological surface. It is fixed through all the rest of this course. And now here I have hyperbolic surfaces. And for each hyperbolic surface, I must choose let's call it H. This is my hyperbolic surface. G is, no, I don't want G because we use G for the genus. M metric. This is the hyperbolic metric. And here I have the surface S equipped with a hyperbolic metric n. What is a marking? This is a marking. Let me try to write a precise formula. A marking of SM is a homeomorphism defined up to homotopy. And now I need you to know this word. So your professor told you what is a homotopy? So this is a homeomorphism defined up to homotopy in the sense that if I modify H by a homotopy, I get the same marking. I get the same marking of this surface. Yes. This surface. I didn't give it a name. Let's call it. Yes. I want a standard surface called X, which is fixed once and for all, and which will serve only for the marking. I don't want. I will not put any geometric structure on this. This is. So before putting the geometric structures here, I need a marking, and I will tell you why. Okay. Let me give a reason in advance. So if I tell you, well, Teichmüller space is the space of all hyperbolic structures on a surface, on a given surface, if I say it like this, then this space is infinite dimensional. Because a hyperbolic surface is just, you see, I can move this hyperbolic structure by some homotopy on my surface. I will get also another hyperbolic surface. Okay. If you think of a hyperbolic surface as a Riemannian metric, you have a scalar product on each tangent space. Then you can move it from point to point, the scalar product, and you can deform it in infinitely many ways. So there's no way that the resulting space is of dimension 6G minus 6, like we said last time. Okay, and the space will be of dimension 6G minus 6. This is the space of hyperbolic structures on S up to homotopy. That is, if I vary continuously a hyperbolic structure on a surface, I don't change anything. I am at the same point in the Teichmüller space. This is something you must understand. Okay, so I will formulate my definition now more precisely. So the Teichmüller space of this is S, G, N, C. This is a surface. This is a surface of genus G with N boundary components and C punctures. The Teichmüller space of this surface is the space, well, of marked hyperbolic surfaces up to homotopy. So I'm complicating a little bit the definition, but this is much more precise. This is I gave you the idea before. Now you must deal with the marking. You see, if you consider the space of the space of metrics on the tori, and suppose this torus is the quotient of a square of the plane, and then okay, I will tell you. You see this figure here. I can turn it, and then I get also a tori. I get also a torus, and so they are isometric because I'm doing the Euclidean metric of the first torus is isometric to the Euclidean metric of the second torus. They are obtained just by some rotation. The rotation preserves the metrics, but it's a different surface. It's a different point in Teichmüller space because the marking is different. This rotation here, which I talked to you about, is not a homotopy. It's not homotopic to the identity. It's yes. Okay, so let me maybe you will understand more when I will say a few things about this. One important thing is that on a marked surface, I can talk about the homotopy class of some closed curve. Okay, from now on, when I say a closed curve, I mean a closed curve which is not contractible to a point. If I talk about this closed curve, I'm not interested in this closed curve which I can homotop to a point. Okay, this is a closed curve. In fact, the term is essential closed curve, but I will delete the term essential. I'm always talking about essential closed curve. This closed curve, I can shrink it to a point without harming the torus. The torus will stay a torus. If I shrink this curve here to a point, then the topology of the torus will be destroyed. Then I will have this here. It will no more be a surface. Okay. So okay, on a marked surface, I can talk about the homotopy class of any closed curve. Any closed curve has now we know that what is a closed curve. It must not be shrinkable to a point. And okay, let us draw some closed curves. Some closed curves on this surface. This is a closed curve, right? It's not shrinkable to a point. You understand this? This is a closed curve. It's not shrinkable to a point. This is a closed curve. This is a closed curve. This is a closed curve. And then I have one here. I have one here. And then I have more. Do I have more? I have many more, right? So you're right. So say I can start with this, and then go. And then here. So this is now a new closed curve, which I obtained from the first one by going like this, okay, etc. The set of closed curves on the surface is a rather complicated set, and I want to show you a first picture. I want to show you a first picture. Okay. So I need the other. I need this thing. Thank you.
Are these curves called essential curves, or is there more?
Yes. Yes. Essential means non-homotopic to a point. Yes. Not not to the boundary. I mean, this is a little bit. Some people consider them also as essential. Some people. Okay. Now let's talk about surfaces. So this is a picture I wanted to show you. And it's drawn by Thurston, in fact. I have these notes from the first lectures he gave on this. He drew here a typical simple closed curve, so more complicated than the one I drew here. And okay. I said that when I say a closed curve, then I want it to be non-homotopic to a point. Then I said this curve here is homotopic to a point, so I don't want it. There's a theorem, in fact. It's a theorem in topology of surfaces. It's one of the first theorem I learned. One of the first theorem I learned. It says that a closed curve a closed curve in the sense we said that is injective. So let me put here. Simple means injective. That is, I'm not considering curve with double points. Just injective. Injective maps from the circle to the surface. Okay, injective maps from the circle to the surface. So, simple injective closed curve on the surface S. He doesn't call it. So is non-homotopic. Non-homotopic to a point. Is non-homotopic to a point if and only if it is not the boundary of a disk on the surface. So, so here, for instance, I told you that this curve I'm not interested in because it's the boundary of a disk. Right? This theorem is not, I mean, it's a difficult theorem. I told you this is the first theorem I learned in, when I started studying surfaces. This is one of the 2 or 3 results which are in a paper by David Epstein called Curves on Surfaces and Isotopies. I think this is the title of the paper or something like that. And it's a paper which appeared in Acta Mathematica. It's a journal. And in the 1960s, I think, this is it is a long paper. So you see, when I told you that I want to disregard these curves because they bound a disk, and then I show you a typical closed curve like this. How do you know that this curve here does not bound a disk? Maybe it bounds a disk. I don't know. I never tried to figure out. Right? So it's in fact it's a question. In fact, it's a problem. I'm not sure if it's completely solved, or you see, such problems may have different kinds of solutions. The problem is to find an algorithm which says when I draw a curve to know whether it bounds a disk or not. So this is a complicated way of drawing a curve. I mean, there will be no algorithm which will solve the problem for this curve like this. But we discussed last time, or the time before, in fact, the fact that a surface of genus 2, a closed surface of genus 2, you can realize it and then C, D, C inverse, D inverse by gluing the 8 sides of an octagon in this way. Okay? We did this for hyperbolic surfaces, but now it's not hyperbolic. It's just, we are talking just about topological things. So I take this Euclidean octagon and I do my gluing. I know that I will find a topological surface without boundary of genus 2. Okay? Now, when I have this method of constructing the surface, well, I can draw curves on this diagram here. For instance, I can start here and go there. It will give me an arc on the resulting surface. Okay, but this point will be identified with this point on the quotient, so I can continue. My goal is so I continue here and A. So then I will start here again. Wait a minute, let me continue. So I started here. I started here, and okay. I can go here, and then the C, where is the C? This goes here, and then I'm stuck here. I will go to the D, and then the D is here, and I must necessarily go to the A, and the A. Okay, no. Let's go here. Let's go here, and then I come here, and then I continue. In fact, I want to continue. I want to continue until I reach a point which is this one. In fact, I could have stopped here. No, I have to do more. I have to do more so that my curve is closed, so that at the end I arrive to the same point, right? So this is a method of drawing curves on surfaces. And then I tell you, well, okay, now when I do such a thing, I mean, you give a method of joining. You want to join the points which are identified. So how do I recognize in my way of drawing like this that the curve is homotopic or not to a point? This is not an easy problem. And it uses the fact, some way or another, you must use the fact which I raised, which tell you that, well, your curve is homotopic to a point if and only if it is the boundary of a disk on the surface. And here I cannot see yet whether the resulting curve is the boundary of a disk on my surface. Okay? This is a typical problem of topology. If you think about this problem and you try to figure out one solution to this problem and so on, then you learn a lot, and then you become a topologist. Okay, so this is one of the things I wanted to tell you, and then let me.
So you all MSc students learn quotient spaces, right? So these identified sides.
So is there no numerical or algebraic invariant for
Yes. Well, this is a very good question. So when you try to classify and so on, you want to find invariance, numerical invariance, or algebraic invariance, or so on. So you say, okay. In fact, these A inverse, B inverse, when you identify them. Thank you. When you identify, no, I don't want this anymore. Yes. I just need the light. Yes. So something which I didn't tell you. In fact, I said, but so when they are on the resulting surface, you have A, B, and then C and D. The A, B, C, D on the resulting surface are generators of the fundamental group of the surface. So our colleague, when he says, when he asks whether there's algebraic invariance or so on, I mean, one of the questions is you have a curve on the surface which is written in terms of the generators of the fundamental group, and this is now algebraic, and you want to know whether it is zero, it is the identity map in the fundamental group or not. So yes, this is related to this problem. I mean, there's a lot to say about this in algebraic topology. Pardon? Yeah, sure. I mean, this is a basic one basic problem in group theory. In fact, it's called the word problem. The word problem, and the word problem is precisely this one. You have generators for the fundamental group, and then you define an element of the fundamental group as a word in the generators. So is there an algorithm to say whether this word is the identity element of the group or not? And there's a huge research on this, people doing group theory from this point of view, the geometric point of view. Then the results say, well, fundamental groups of surfaces have a solvable word problem. That is, there are algorithms to know if an element of the fundamental group of a surface is the identity element or not. This is a solvable problem. But there are groups with non-solvable problems, and there are complications and so on. So this is, these are central problems. You know, when we start thinking about curves on surfaces, we hit complicated research problems. Okay, so so why am I talking about this? Let me remind you that we talk about a marking of a surface. In fact, to define the marking, I tried to do it precisely. It's always more complicated than what is the real matter. You see, I have a surface. Again, I have this surface, and I have this curve, and I have this curve. What is the difference between this curve and this curve? Is there any difference between this curve and this curve? I'm not talking about the length of the curves, just these two curves as closed curves. Huh?
Are they homotopic? That's what you asked?
Yes. So your professor says these curves are not homotopic. So, but when I defined the surface, I didn't. So talking about a marking from a given fixed surface to this one here will allow me to say that well, this curve is different from this curve because they correspond to different homotopy classes in a fixed surface. So these curves are not. So you see, these curves are not homotopic, but I may have. You see a hyperbolic structure. I may have a hyperbolic structure which is very symmetric with respect to this plane here or to this curve here. That is, there's an isometry. There could be an isometry. Which takes me this part of the surface to this part of the surface, but still, even if geometrically the two surfaces are the same geometrically, if they are isometric, I want to say that this curve is different from this one. Why do I want to say this? Because there's something called the length spectrum of a surface. So among the people who know, can you tell me what is the length spectrum of a surface?
It's the length of the path of the code path.
Yes. So the length spectrum, there's the word length here. So this is the set of lengths, well, of the simple closed, yes, geodesics. Here, let's say I have a hyperbolic surface. And one thing which is true, if you say it precisely, is that the length spectrum of a surface determines the isometric class of the surface. It determines the geometric structure. So a hyperbolic surface, I can characterize it by the length of its simple closed geodesics. But here, in fact, the length structure of I want to put marked hyperbolic surface length of because for me this, you see, this even if there's some isometry which may take this side to this side, but I want to consider them as different surfaces, and this is why I introduced the marking. So here I want to say that this is the interesting part, the marked length spectrum. When I have a surface like this, I want to tell you, well, the length of this closed geodesic is 2. The length of this closed geodesic here, when I have a hyperbolic, when I have a metric, I can measure lengths. I can measure lengths of curves. Okay, hyperbolic metric. Well, a metric on some space allows me to measure distances between points, but it allows me also to measure lengths of curves in the usual way, in the way Archimedes did, in the way by taking points here, measuring the distance between this and this, measuring, and then taking more closer and closer points. And this is, this is what you learned in whatever, in measure theory or in even in Riemannian geometry. You see, well, how do you measure the length? When you have a metric space, you measure the length of a curve by taking points and then approximating your curve by taking closer and closer points. And if it converges, then you say that the length is finite. Anyway, so the important thing is that the important thing we have to remember. The important thing we have to remember is that again, a marked hyperbolic surface, I'm going to write the same thing because it's important, is determined by its marked length spectrum. So let's now write again this definition. The Teichmüller space of topological surface of genus G, say with n punctures and C boundary components, but let's stick to this case without complicating with functions and so on. Teichmüller space. Now this is the space. Now I want to put homotopy classes, because I told you that if two hyperbolic metrics, or if two metrics are homotopic, I consider them as the same. Otherwise, my space is infinite dimensional. Homotopy classes of hyperbolic metrics on of, I have to put the marking somewhere, of marked hyperbolic metrics on SG. And this is the most precise definition. Now I didn't cheat you. You have, we didn't forget any word here. Because again, if I don't put the marking, I will tell you, okay, it's homotopy classes of hyperbolic structures, but how will you distinguish this metric from an isometric metric, or from okay. So this is the definition now, and then the standard notation here is T with a calligraphic T of SG, or TG, or T if the G is understood. Now we have a space. You have an idea of this space. So on TG, I have functions, and this is very important. When you have a space, you want to study functions. So you know now some functions defined on this space. What are these functions? No. The homeomorphisms are okay. I mean, usually when I say a function, it's a function which goes from the space to some numerical space. Yes, tell me. Yes, the length functions. These are the length functions. The length functions the length function associated to simple closed curves. So what are these length functions? Can you tell me more precisely what is this length function? The length of what? Yes. Yes, right. And here we need a result which you must know. So in fact, in each homotopy class of simple closed curve, there's a unique geodesic. There's a unique shortest curve. And when I say the length function associated to simple closed curve, it is the length of the unique geodesic in this homotopy class. Let's write it here. This is not difficult. In fact, this is a proposition. In any homotopy class, of simple closed curves, there's a unique geodesic. Remember, we said simple closed curve means that it's not shrinkable to a point. So, for instance, this one here, I have a unique geodesic. This one here, I have a unique geodesic in this class. So, how do you prove this? This needs a proof, and the proof is not very difficult. In fact, it's a general theorem for negatively curved, not only hyperbolic, but for all negatively curved manifolds. It's an old theorem. In fact, it goes back to Hadamard. He has a paper where he proves this even for variable negative curvature.
Unique theorem.
Yes, a unique geodesic. So the existence is not. I mean, it's the proof is standard. You take the shortest curve, and you show that this shortest curve is a geodesic in the sense of hyperbolic geometry. In fact, this is not difficult. But you want to say that the shortest curve exists, that there exists a shortest one, and this is general topology. I think by applying Ascoli theorem or things like that, you know, you have curves are of bounded lengths, and then the uniqueness is not completely obvious, but you have to prove it. So the uniqueness yes.
Parallel curves.
Yes.
Seems like this.
No, because the long tube it has always this form. Yes. Well, funnel means that goes to infinity. No, but here it's. If you have a long tube, then there is only one. This is, you see, let me tell you why. In fact, you talked about universal cover, right?
Yes.
Okay, so all these surfaces we are talking about, they have the same universal cover, which is the hyperbolic plane, or this disk model. I want to talk about this disk model. You see, this behavior like this of geodesic coming close in the hyperbolic model, the geodesics when they come very close, then they necessarily diverge, and you have only one shortest distance between them. You can prove this if you know a little bit of hyperbolic geometry. In fact, what I told you is sufficient to prove that you have this situation. And likewise, when I said that there's a unique geodesic, why is there a unique geodesic? Well, let me draw. Let me draw here a random surface. And suppose that in some homotopy class, I have two geodesics, two closed geodesics. So this is one, I represent them symbolically, and then this is second one. You see? So this is a geodesic, and this is a geodesic, and I have a homotopy between them. I have a homotopy. There's a family of curves which takes me continuously from one to the other. This is a geodesic. This is a geodesic in the surface. It necessarily is the quotient of some geodesic in the hyperbolic disk, right? Right? And this is also the quotient of some geodesic in the hyperbolic disk. And okay, so I made them intersecting here. Okay. And you see, this homotopy between this one and this one, it necessarily gives me a homotopy between the homotopy. You see, these curves, the homotopy will take this curve to this curve, bounded homotopy, right? And this bounded homotopy, when I look, so everything that happens in the universal cover is a covering of something which happens on the surface. Then it would give me a bounded homotopy between two curves there, which is not possible because they intersect in this point, and their points at infinity are infinitely far from each other, and there's no bounded homotopy here. This bounded homotopy on the surface would give me a bounded homotopy between two geodesics there, which is not possible. And the same if the curves were disjoint. In fact, it's the same thing. If I had two curves, like you said there, and why couldn't be two geodesics, which would be yes, the same argument, because these two geodesics, which bound an annulus here on the surface, would bound an annulus in the universal cover, because the annulus, you know, I'm not talking about an annulus like this, because here the distance is infinite, is going to infinity from here to here. So I would have two geodesics in the universal cover which converge to the same point, which is impossible. In fact, we know that in the hyperbolic plane, if I take 2 points on the boundary, there's a unique geodesic between them. Okay, so this is important. And now I state this. Yes.
Do these unique geodesics
converge
to the boundary of pairs of bands?
Now, if the pairs of pants, no. There are geodesics which converge to boundary of pairs of pants, but not this one. This is just a unique closed geodesic in some homotopy class. So your friend here is asking, you know, I had this picture at the beginning of my lectures, and with geodesics converging to boundary of pairs of pants. No, this is not. This behavior would be just in the universal cover. You have. So this curve here would have a lift here. This curve here, which converges in this to this boundary of the pair of pants, would be like this, like this, and then from the other side it converged to the lift of this geodesic, which would be this one. So, okay, but it cannot converge to. So, in other words, it does not. It cannot converge from both sides to the same boundary of the pair of pants. It's spiraling along different boundaries.
So all hyperbolic surfaces have the same universal curve.
Yes, all of them.
Doesn't matter how genus punctures.
Doesn't matter how genus or punctures. Yes. Surfaces with boundary, this is a little bit different because because you have boundary points. You have boundary points, and the universal cover also must have some boundary. So the universal cover of this is part of this hyperbolic disk.
Hyperbolic disk or hyperbolic plane.
Or hyperbolic plane, yes. Yes. So let me let me say this important statement. Let me say this important statement that on this Teichmüller space, Tg or T, I have length functions associated to simple closed curve, lengths of closed geodesics in each homotopy class. Okay. I said that length functions and the length functions, how many length functions I have? I have infinitely many, right? Because the homotopy classes of the simple closed curves, I have infinitely many homotopy classes. You see, as I said, I have my surface. This is a homotopy class of a simple closed curve. Then what I can do here. This is another homotopy class, and then I can twist again and again and again. I get infinitely many. I cannot do the pictures, but okay.
This is free group also.
No, not free. There is one relation. It's one related group. If for surfaces with boundary, it is free group, but for closed surfaces, there is one relation. So you see, we had this picture of the right. So if the surface is like the one before, obtained by gluing the sides of an octagon, then we had A, B, C, D, and so on. So this A, B, A inverse, B inverse, C, D, C inverse, D inverse. If you do this product, then it bounds a disk. It's homotopic to a point. So for a general surface, it is a group with A, B, C, D, E, F, and then with one generator, A, B, A inverse, B inverse, C, D, C inverse, C, D, etc., etc. So 4 by 4. The resulting is null homotopic. So these are special kinds of groups called groups with one with one relation, one relator group, and they have a special study. I mean, there are hundreds of people who study just these. Hundreds of people now which study these groups with 2 n generators and one relation. So I was saying here that I have length functions. The length functions associated with simple closed curve, and I insisted on the marking. The marking is the thing which distinguishes the simple closed curve with from one to the other, one from the other. Okay, and then I said that I have infinitely many simple closed curves, right? You remember this? I said that I have infinitely many. I tried to draw a few. You see the infinitely many homotopy classes of simple closed curves. The length function associated with homotopy classes, I forgot to say this. Classes of simple closed curves. Let me remind you of something. Before I continue there, let me remind you of something. I showed you a construction of hyperbolic surfaces. I told you that you can do this by gluing pairs of pants. You remember this? And I showed you that, okay, for a given pair of pants, I can obtain it by gluing hyperbolic. Now I have hexagons, right-angled hexagons. We did this construction with right-angled hexagon. This is one right-angled hexagon, and then there's another right-angled hexagon from the other side. And then you see, I can take two of these. Two of these pairs of pants. What do I need so that I can glue this side to this side? Yeah, I need them to have the same length. If they have the same length, I can glue without problem. If I don't have the same length, so okay, so I can I have these parameters, and suppose so I glue this one with this one with this one, and this one with this one. I get a closed surface of genus 2. And now in this closed surface of genus 2, I use these hexagons and so on. So you must be almost sure, in fact, that I must have at least, in these length functions, length function of associated with simple closed curve, I have this 1, 2, 3, and then here the same. I have 3 length functions which present themselves immediately to me and which are important. So these 3 length functions, okay, you have 3 length functions. What other length functions do you have on this? What other closed curves you see on this surface? Well, this one here, since it is perpendicular, it goes with this one here, and then it closes. So in fact, I don't have 3. I have 6. Okay. And now I ask the question: do these 6 length functions of closed curves, simple closed curves, do they completely determine the hyperbolic surface? Do they completely determine the hyperbolic surface? Yes, so your friend here says no. it's not. The answer is not obvious. No, no. In fact, if I take a surface here now, I take a surface here of genus 2, and I tell you, well, I know the length of this curve. I know the length of this curve, and I know the length of this curve. Here I have 3, and then 3 more. The length of this closed curve, the length of this closed curve, and then again the length of this closed curve. Does it determine completely my hyperbolic structure? This is a very good question, in fact, and it was an interesting question. In fact, it was an open question for several. I mean, it lasted a few years, not too much, because it's not very difficult. Not very difficult. You remember I told you that the Teichmüller space of a closed surface of genus G. What is the dimension of this space? You remember? What is the dimension of this space? Yes, 6G minus 6. And the good question is whether I can find 6G minus 6 closed curves, homotopy classes of closed curves on the surface, such that if I know the length of these 6G minus 6 closed curves, then the surface is completely determined as a marked surface. And there was some work on this. Some people showed that you need more than 6G minus 6. You need 6G minus 6 plus something. And then it was less and less. And finally, the result, I mean, the theorem is that you need 6G minus 6 plus 1 curve. You need one more curve than the dimension, so that, yeah, this is a result. It's uniquely determined. Uniquely determined, yes, uniquely determined. Uniquely determined. So this is to show you the importance. So I have a big space, Teichmüller space, and I want to find parameters for this space. Yes, in 1 minute I will. Okay, no, maybe after the break, because it's a little bit long. Okay, after the break, I will explain to you more about it. Yes?
Mariam Lisa can include something about simple closed curves, counting of simple closed curves.
Yes, so she's asking me about the proof of, I mean, you see, when I draw my surface, then I always draw the same kind of same simple closed curves, or a little bit more complicated this one, or a little bit more complicated, and then I try to draw a little bit more complicated, and I drew one, but I was failing. So this is Thurston here. Okay, how do I do this?
The one you drew earlier, right?
Yes, the one I drew earlier. The one I drew earlier.
These things take time.
Yes, it is coming. Okay, so this is simple closed curve, and let's suppose that it's this picture only suggests a homotopy class of simple closed curves, right? But in this homotopy class of simple closed curve, if the homotopy class, if the curve is not homotopic to 0, then it has a length. the smallest curve in this homotopy class, the unique geodesic in this homotopy class, it has a length, right? So every simple closed curve, whatever complicated you draw it, will have a unique geodesic representative. And your professor asked me about this problem of related to the work of Mirzakhani, of course. So if what is the growth rate of the length of simple closed curves? So if I tell you, if I have a surface of genus 2, how many simple closed curves I have whose length is less than 1,000 or 2,000? Of course, it's not in terms of numbers, but you ask whether the growth is exponential or something else, or yes. So this is the problem of the growth rate of the length of simple closed curves. It's important because, as we said, giving the length of the simple closed curve determines the surface completely. So now the next question is about the growth rates of the other curves. So here, for instance, when you glue these two pairs of pants to have a closed surface of genus 2. Okay, now I want to draw the other simple closed curves on this surface. So you see in hyperbolic geometry, in the hyperbolic plane, when you have a line, then you have another line. Another line, either it coincides or it cuts it transversely. It cannot be tangent, and it cuts it here one time. So here I have another curve which when it starts here, it must go here, it must go here, it must come here, and then it must come here. And then you want an algorithm. That draws for you simple closed curves. That is, you don't want the curve to intersect itself. So at some you don't want this to happen. You want curves with which are non-intersecting. You want an algorithm which gives you curves which are non-intersecting. And then when you find that this problem is too hard for you, or when you find that, okay, everything is known, in fact, on this problem, then you ask about closed curves which have one intersection point, only one intersection point. And this, I can tell you that not many people know a lot about this. I'm looking at closed curves, not simple, not injective, but with one intersection point. So, for instance, this one here, then 1 point, only 1 point, and then injective. Yes, yeah, you can leave it because okay. So we a little bit of.